Welcome to Grade 12 Artificial Intelligence. In this module, we study how an agent can learn good behavior purely from the rewards it receives, and what happens when many such agents learn in the same world at the same time. This is the foundation of modern decision-making systems, from game-playing programs to traffic and energy control. Here is our plan for the lesson. We'll begin with how a single agent learns from reward and define what we mean by a policy and a value. Then we move from one agent to many and borrow some ideas from game theory, including the Nash equilibrium. We'll see how reinforcement learning extends to many agents and meet policy gradient and actor-critic methods before naming the hard problems that make all of this difficult. Reinforcement learning describes an agent interacting with an environment step by step. At each step, the agent observes the current state and chooses an action according to its policy. The policy, written as the Greek letter pi, is the agent's rule for mapping a state to an action. The environment response. It returns the next state and a single number called the reward, which says how good that step was. The agent's goal is not to grab the largest reward right now. It is to maximize the return, the total reward accumulated over the long run. We capture how good a state is with a value function, the expected return from that state onward. Reward says what is good, value says what is good in the long run, and that distinction drives everything that follows. So far, one agent faced a fixed world. A multi-agent system places several agents in the same environment, each with its own actions, rewards, and policy. The crucial shift is this. From any one agent's point of view, the other agents are now part of the environment. Their interests might align, so they cooperate, or conflict, so they compete, or sit somewhere in between. The outcome no longer depends on your action alone, but on what everyone does together. And because the others are also learning, the world no longer stands still while you improve. To reason about that, we borrow the language of game theory. Game theory studies decisions where each player's outcome depends on the others. Consider the famous prisoner's dilemma. Two players each choose to cooperate or to defect, and the table shows the reward each one receives. If both cooperate, each earns 3. If both defect, each earns only 1. But if one defects while the other cooperates, the defector earns 5 and the cooperator earns nothing. Now think like a player. Whatever the other does, defecting earns you more. So both defect and both end up with 1. That outcome is a Nash equilibrium, a choice of actions where no player can do better by changing their own action alone. The lesson is sharp. Individually rational choices can lead everyone to a worse result than cooperation would. Multi-agent reinforcement learning, often shortened to MARL, combines the two ideas we have just met. Several agents learn at once, each shaping its own policy from the rewards it receives. We classify these settings by how the rewards relate. In a fully cooperative setting, the agents share a common goal and a common reward. In a fully competitive setting, one agent's gain is exactly another's loss. Most real systems are mixed, with both cooperation and competition present together. Notice what the goal becomes. With other learners in the world, we no longer seek one single best policy. We seek a stable set of policies, an equilibrium, where each agent is doing as well as it can given the others. How does an agent actually improve its policy? One powerful family is the policy gradient method. Instead of learning values and reading off a policy, we represent the policy directly and nudge it in the direction that raises expected return. In practice, that means increasing the chance of actions that turned out better than expected and decreasing the chance of those that turned out worse. The actor-critic method splits this work in two. The actor is the policy that chooses the action. The critic is a value estimate that scores how good the action was. The critic computes the advantage, how much better an action was than the average for that state, and the actor uses that signal to learn. Actor and critic improve together, each making the other sharper. Why is many agent learning so much harder than the single agent case? The first problem is non-stationarity. Because the other agents are also learning, the environment each agent faces keeps changing underneath it. A policy that was best yesterday can become poor today, simply because the others have adapted. The second problem is credit assignment. When a team of agents shares a single reward, it is hard to tell which agent's action actually earned it. On top of that, the number of joint actions grows explosively as we add agents, so the space to search becomes vast. These are why stable multi-agent learning takes careful design and not just more computing power. Keep these two names in mind, non-stationarity and credit assignment. These ideas are not only theory, they already run real systems. In Kigali, reinforcement learning agents can control traffic signals at neighboring junctions, coordinating their timings to ease congestion across the city. In the United Kingdom, software agents help balance the energy grid, matching electricity supply to demand from moment to moment. In warehouses across the United States, fleets of robots learn to route packages and avoid one another while sharing the same floor. Financial markets, too, are full of trading and pricing agents reacting to each other's moves. In every case, the same challenge appears. Each agent is learning while all the others are learning too. Before we recap, let's clear up the common misconceptions. First, the reward is only the signal that defines the goal. It is not the agent's plan and not its policy. Second, a good agent maximizes long-run return, not the single largest reward in front of it. Third, a Nash equilibrium is stable, but it need not be the best outcome for everyone, as the prisoner's dilemma showed. Fourth, adding agents is not the same as making one big single agent problem. Non-stationarity changes the problem in kind, not only in size. And finally, a policy that has settled or converged can still be beaten by a rival that keeps adapting. Hold on to these, and the rest of the field will make sense. Let's gather the key ideas. Reinforcement learning is an agent learning from reward through a loop of states and actions. The policy maps states to actions, and the value function scores the long-run return. With many agents, each becomes part of the other's environment. A Nash equilibrium is a state where no agent gains by changing its action alone. Multi-agent learning may be cooperative, competitive, or mixed. And the two hard problems to remember are non-stationarity and credit assignment. Now let's check these ideas with 3 quick questions. Here is the first question. In reinforcement learning, what does the value function estimate? The reward is the signal for a single step. The value function estimates the expected return, the total reward gathered from that state onward. So the value function captures the long run, not just one step. Question 2. In the prisoner's dilemma, why do both players end up defecting? For each player, defecting earns more than cooperating, whatever the other one chooses. Since neither can do better by changing alone, both defecting is the Nash equilibrium, even though both would prefer mutual cooperation. Last question, and it ties the module together. Why is multi-agent reinforcement learning harder than the single-agent case? The central reason is non-stationarity. Because every other agent is also learning, the environment one agent faces keeps shifting beneath it, so a policy that was best can stop being best. Credit assignment, sharing out a common reward, makes it harder still. Excellent work. You now understand how an agent learns from reward, what a policy and a value function are, and how everything changes when many agents learn together. You can read a payoff matrix, name a Nash equilibrium, and explain why non-stationarity makes multi-agent learning hard. In the next module, we'll scale these ideas up with deep reinforcement learning. I'll see you there.